A while back, one of those oddly satisfying Tetris Splendor animations popped up on my feed. However, instead of enjoying it like a normal person, I thought, yeah, I could probably code that. That's when I decided to make one of the worst decisions of my life, to spend more than 7 hours trying to make a soft body physics engine from scratch. Now, you might wonder, why should we care about deformable objects? Well, contrary to traditional rigid body physics where objects maintain their shape, soft body physics allows objects squish, stretch, bounce, and jiggle in all the ways reality demands. For that, we'll be implementing XPBD, aka the Extended Position-Based Dynamics paper, as a method to solve our constraints and make our soft materials behave consistently regardless of how fast our simulation runs or how many calculation steps we take. First things first, I had to actually see something. Here, as you can see, I'm having a bit of trouble making my OpenGL scene, but I eventually got it to work with a 15 by 15 floor. Not much, but it's home. And alongside that, we also add a basic render function and a few placeholders for later controls. We can now begin the interesting part. For our soft body, we'll use a simple cube. However, to make this cube, we cannot actually model it as a single solid box. Instead, we'll treat it like a collection of point masses, aka particles, connected by springs, or in other words, constraints. Pretty much like this. To define this cube, we start with 8 vertices positioned in 3D space. Each particle has the same mass since we're creating a uniform material. Then, we can connect the adjacent vertices with distance constraints, creating the edges of our cube. In a few seconds, when we make the actual physics engine, we'll force these constraints to try to maintain their original distances between connected particles. The constraints work pretty much as you'd expect. Try to compress it, it generates a force to try to prevent you from compressing further. The more you compress, the more force it generates. Try to stretch it out, and the opposite happens. With the cube setup complete, we can move onto the physics engine, implementing extended position-based dynamics. Traditional position-based dynamics has a fundamental flaw where the stiffness of materials depends on your simulation time step and iteration count. Make your simulation run faster, and suddenly your rubber becomes steel. This makes it nearly impossible to create predictable, reusable materials. In the XPBD paper, this is solved by introducing the concept of compliance, which comes down to essentially how much a constraint is allowed to be violated until a correction is applied. Let's begin with Newton's equations of motion, where m is our mass matrix, x represents positions, and u of x is our energy potential. The key insight of XPBD is expressing this energy potential in terms of constraint functions. Here, c of x is our vector of constraint functions, and alpha is our compliance matrix, which is also the inverse of our stiffness. Higher compliance means softer materials. The real breakthrough comes from introducing Lagrange multipliers to decompose forces, where alpha tilde equals alpha divided by delta t squared incorporates our time step. This gives us a way to track the total constraint force throughout the simulation. Okay then, let's look at how we implement this step by step. First, we apply the external forces. Gravity acts on each particle, accelerating it downward. Simple enough. Then, we try to predict the positions. Using Verlet integration, we predict where each particle will be. Next, we solve the constraints using the method present in the paper. For each constraint, we calculate how much it's being violated and apply corrections. To do this, we can use the formula for a single constraint present in the paper. Don't worry, I barely understand it too, but we can break it down into c of x, which will be our constraint violation, basically how far we are from the desired distance. Alpha tilde times lambda, which accounts for the compliance and accumulated constraint force. And the denominator, which includes both the mass-weighted constraint gradient and compliance. The position correction can then be solved as follows. Cool. With that done, we update the velocities. We update velocities based on how positions actually changed. And finally, we handle collisions and damping. By doing this, we prevent particles from falling through the ground and apply slight damping to reduce oscillations. The beautiful thing about position-based dynamics is that it gives us consistent behavior regardless of time step or iteration count by allowing the compliance parameter to directly control the material's stiffness in a physically accurate way. Great. Now, let's see how it all looks in code so far. First, we're initializing the class and particles and placing the constraints in place. Next, we define a few functions to get and set particle positions so that we can manage them outside of the physics script. We also add a few functions to continuously apply gravity to particles and predict their future position based on velocity and position. This is important so that we can check for grounded particles, etc., etc. Then, we solve the constraints. This is essentially what we were just talking about. Here, we follow the constraint and position correction methods that we took from the paper and apply them in code like so. After that, we add a few functions for velocities updates, damping, and ground collision. And finally, we can pack all of these functions into the step function so that it's ran every tick all at once. With our body configuration and physics engine complete, we wire everything together in our main simulation loop. The integration is straightforward. We initialize our cube configuration, pass the vertices and constraints to the physics engine, and then run the simulation loop. Each frame we call physics step to advance the simulation and then render the current state. The mouse controls let us orbit around our creation and watch it in action. As we run our simulation for the first time, we can finally see the cube. However, you may haven't noticed, perhaps because I'm such a great programmer, but the cube collapses on impact with the floor. The issue lies in our constraint topology. We've only connected adjacent vertices with distance constraints. This can be easily fixed by adding a diagonal constraint to each face. There. The cube now looks and feels much more solid. I've also added a little jumping function that applies an upwards impulse to all the particles, giving it a slight jump boost. I decided to also add something to debug our simulation. To better understand what's happening, force vector visualization is added so that we can see what forces are being applied to what particles, and with how much intensity. This visualization reveals the internal dynamics of our soft body. When a particle is pulled away from its rest position, you can see the constraint forces pulling it back, creating the springy, elastic behavior we expect from deformable materials. Very well. Now the core of your engine is done. Next up, I'll add actual faces in between the constraints of the cube so that it's no longer just a wireframe. Great. Now let us create a small grabbing engine so that we can grab our cube and play around with it. Here's how it works on paper. When the mouse is clicked, we shoot a ray from the camera through the mouse position into the 3D space. Next, we test this ray against all triangular faces of our cube using the Muller-Trembor intersection algorithm to detect if we have hit our cube or not. If we do hit a face, then temporary constraints are created connecting the hit point to all three vertices of that triangle. Now, as the mouse is dragged, we project that movement onto a 2D plane parallel to the camera, updating our grab point in 3D space. We do this so that the mouse controls can feel smooth and enjoyable. The physics engine automatically handles the rest. As the hit point is dragged with the mouse, the grab constraints pull the cube vertices toward your mouse, creating realistic deformation as the material resists being stretched or compressed while following the mouse. Great, we can now move the cube around. However, there is a problem here. You may notice that sometimes the cube kind of just collapses a bit on itself when it hits the ground in weird angles, almost as if it was very poorly inflated. This happens because up to this point, all of our constraints are just distances along edges and diagonals. They keep edges stiff, but they don't actually guarantee that the cube preserves its volume. The solution to this problem is to quite literally inflate out cube with volume constraints. This way, instead of only keeping edges in check, we explicitly require that the cube's interior volume remains constant. To calculate the volume constraints, we first split our cube into 5 tetrahedra. each tetrahedron has a well-defined volume, and we can enforce that this volume stays close to its initial rest value. Let's define our tetrahedron by the vertices P0, P1, P2, and P3, such that the signed volume is given by the scalar triple product, like so. This is exactly the formula you see in the code. For each tetrahedron, our constraint function is. With this in mind, we can calculate the volume gradients. In the XPBD paper, we need the gradient of this constraint with respect to each particle position. For a vertex opposite a triangular face, the gradient is simply the area normal of that face divided by 6, where Ni is the outward normal of the face opposite to vertex I. Here, J, K, and L are the 3 other vertices forming the opposite face. After all this, we apply the volume corrections to each vertex, like so. Where Wi equals 1 divided by Mi is the inverse mass of vertex I. W sum is the sum over all vertices of Wi times the squared length of the gradient of C with respect to Pi. And alpha equals alpha naught divided by delta T squared is the scaled compliance parameter controlling volume stiffness. These volume forces work like internal air pressure. The compliance parameter alpha controls how inflated our cube behaves. Lower alpha means stiffer volume preservation, like a rigid balloon. Higher alpha means softer volume preservation, like a partially deflated balloon. And there you have it. This is the final ingredient that makes our soft body cube behave believably under gravity, collisions, and user interaction. And finally, there we have it. A soft body physics engine built from scratch based on the extended position-based dynamics paper and my humble attempt at doing physics math. I remind you that all papers mentioned and source code are available in the description. I highly appreciate the support you've been giving on these past videos, and if you haven't already, consider watching them. They're pretty cool. As always, feel free to drop a comment with your thoughts or ideas for this or the next project. And with that, I hope to see you on the next one. Goodbye, guys.